Hi everyone. Today we are going to start to a new topic about the root locus in control theory. Okay? And so in the section 1 we search the answer of this question, just like this one. What is the root locus? This is the first case for our lesson, okay? But in order to understand the meaning of the root locus, we need to explore the some open loop and closed loop transfer function in control theory, okay? And so, as we always do, we need to define the R problem in here, just like this one. In the open loop, TF can easily be found they are not affected by the gain. What's the meaning of this? For example, if we have any input signal in here, just like this one, and so we can apply the K in here, and also we may have this kind of plant in here. And also we can create a dynamic response of this system, okay? But in the collection of this form, we have the K times B divided by S plus A is given in here. The denominator of these terms directly related to the transient or steady state response. This is the amplitude gain in here. If we change the K value in here, just like this one, and then we will get the different amplitude, but not the dynamics or the transient response of these control systems, okay? These are the case for the open loop, and so we can easily set any parameter in the open loop transfer function. But in the real life, we don't have this kind of systems, because in every mechatronic or the control systems we have the feedback or the closed loop transfer function in order to control the parameters in here, okay? And so we can define the other terms in here, just like this one. However, closed loop has this kind of relation, Rs plus minus, and so we have some simple gain K in here, and GS and CS can be given in here, just like this one, okay? And so we have also HS. This is the feedback part. Remember, this is the measurement or the sensor of your system, okay? And so these are the plant, and so we have the changeable K or the gain coefficients in here. If we solve this equation, we will have the RS, the input signal in here, just like this one, and so we have the closed loop transfer function in here, just like this one, K times GS divided by 1 plus K times GS times HS, okay? These are the closed loop transfer function in here, but just examine these results. In the denominator of this part, affected by the changing with the parameters of the K, okay? And so they are affected by the K, or the pole location can be changed by adjusting with the K parameter in here. For example, if we set the GS is equals to the 1 divided by S plus 1, and so we can take the HS is equal to the 1, and the whole closed loop transfer function, which is given in the KGS divided by 1 plus KGS and hs, and so we will get to the what? This solution in here. Ts is equals to the what? K times 1 divided by s plus 1, this is the gs, 1 plus k times 1 divided by s plus 1. Okay? If we reorganize the whole equation in here, we will get the what? The k divided by s plus 1 plus k. Okay? Or we have the k divided by s plus 1 plus k. Okay? And so, what is the pole of this system? The pole P1 is equals to what? The minus 1 plus k on the what? The root locus or the S-plane. Okay? And so, the dynamic response can be changed with the what? With increasing or decreasing values of the what? The k value. If we have the high enough k in here, and then our system faster than the normal one. Okay? If we decrease the values of the k, and so we get the slower transient response in here. Okay? So, what's the conclusion of these terms? These terms states that the transient response is changed, or the dynamic response or the time response is changed in here. Okay? In the closed loop transfer function. Okay? So, how can we define or how can we select the proper values of the k? By using this nomination, because if we affected by the k, and then we need to organize our k values in here, and so the solution is simple. Solution is simple. Using root locus to define the stability of your system or the dynamic response. For example, Ts, for example, percentage of the what? The overshoot value, or peak time, and blah blah blah, or the steady state error. Okay? And so, in order to analyze this system, we will look at to the what? The vector notation of the complex number. We will review it. Okay? Firstly, just remember that we have the S is equals to sigma plus J times omega, right? This is the real part and this is the imaginary part, right? And so we have the S-plane. Just remember, this is the S-plane, right? And so we have the J, W, and sigma. And so in the time response analysis, this S-plane is utilized to what? To define your time response. For example, if you have the higher negative values of the roots in here, and so we can say that our system is fastest. Or if we have any J term in here, oh, okay, this system is underdamped or the oscillate in time, right? And so, if we have this notation in here, just like this one, and so we can define any magnitude in here, just like this one. And so we can create the theta value in here in the polar coordinates. And so we have the sigma value and also W value in here. And then we can define these terms in here, or we can show this term just like this one in the polar coordinates, okay? These polar coordinates determines the time response of your closed loop or the open loop transfer function or your system. Okay, and so the polar coordinate is utilized in the frequency analysis. Okay, for example, if we have the any system with the roots of the what, these terms, for example, if we have the s plus 7 in here with the s is equals to the what, the s plus j2, and so we have the minus 7 in here just like this one, and j2 is given in here, and 5 is given in here, and so we can draw this line in here. Okay, in the frequency analysis we can use these terms, but the root locus shows us the closed loop stability of the characteristic equation when k is the change. Okay, and then we can design the transient response and also stability of the closed loop system, because if we have the any k value in here just like this one, we can change the pole location on this s-plane. Okay, and so if we have this s-plane, this is the s-plane with the variable k, we can say that this is the root locus. Okay, this is the basic representation or the definition of the root locus in here. Okay, so any question? Okay, if you don't have any question, and then we can give some simple example in order to understand the root locus techniques. Suppose that you have the system CL like the what, the RS value in here just like this one, and so we have feedback in here, and so we have also a K1 gain, and also we have the transfer function in here, K2 divided by S plus 10. Okay, and also we can get the what, the C S in here. Okay, this is the unity feedback. Okay, and so our system is given in here, but in the closed loop formation we have the RS is feeding in the closed loop transfer function in here just like this one, and so K S square plus 10 S plus K, and so K is equal to the K1 and K2. This is the adjustable parameters in here in the closed loop notations. Okay, in order to understand how can we change the poles of the system, we need to write to these parameters K, pole 1 and pole 2, because if we have the second order system in here just like this one, and so we have two poles. For example, if we have the S over 3, we have the what? We will have the 3 poles, pole 1, pole 2 and pole 3. Okay, and so firstly, if we choose the K is 0, and then we have the poles in here minus 10 and the 0, because this is 0, S times S plus 10, and so pole 1 S10 and 0. If we have the choosing the K is equals to the 5, and then we can get the minus 9.4 and minus 0.5. Okay, and also we can change the K as equals to the 10, and so minus 8.8 and minus 1.1. These are the roots coming from the what? This characteristic equation. Okay, and so if we choose the 25 in here, and so S square plus 10S plus 25, and so this yields us to what? The minus 5 and minus 5. And so if we have the 30 values in here just like this one, and so minus 5 times J 2.2 and minus 5 minus J 2.2, right? And so if we choose the 50 values in here, and so minus 5 plus J5 and minus 5 minus J5. Okay, these are the roots of the R systems for changing the K parameters in here. Okay, so we can change the K by using the arbitrary way in here. We can choose also the 100, but how can we visualize these results in the graph? For example, if we can draw, if we draw these equations or the values in here, just like this one, sigma and JW, right? And so how can we do that? We must firstly know that if we choose the K is 0, and then we have the one pulse in here, right? Because the RGS function S and S plus, right? This is the 0 root coming from the plant, and so we have also minus 10 from the GS, right? We can assign these parameters in here. Okay, and so after that, just see that this K is increasing up to 25. We get the 5, minus 5 and minus 5 in the closed loop response of this system. This is the closed loop response. Okay, and so we have also, for example, minus 5 in here, and then after the minus 5, the real part of the R pulse does not change, only changing in the in the imaginary term. Okay, and so if this is the case, and then we can draw this line in here at the at the minus 5, because if we increase the K value in here, and then we can increase the imaginary part or the oscillation part of the R graph in here, just like this one. Okay, so what is the values of these terms? K at this moment is the 25, but if I increase the K, if I increase the K up to 50, and then we will get to J5, right? And also we have the K 50 and minus J5. Just using this table, I can draw the whole things in here just like this one. For example, this is the K25 and K30 and K40, right? And so also we must use the values of the K below the 25. Just see that our pulse is going to the minus 10 to minus 5. Okay, I can see that this line should be given in here just like this one, and on the other side we have the 0, minus 0.5, minus 1, minus 5. Okay, and so also we have another line in here just like this one. Okay, and so if the K is equals to the 5, and so for example we have the minus 1, right, or 0.5, and we have the K is equals to the 5, and we have minus 9.4, right? And also we have the K is equals to the 10. This roots indicates the minus 8.8, but in the K is equals to the 10, and so we have the minus 1.1. Okay, and so these red lines called root locus. Guys, these red lines always closed loop response of your system. Okay, do you understand how we can draw the root locus on the S-plane from this nomination? Please write the chat, okay? If you have any question about this. Do you get it? The complete notion of the root locus. Please react me, guys, because it's the important. Okay. So we can set the characteristic equation poles in terms of different k values at the S-plane by using what? The root locus. The general name of this plane or the roots is calling the what? The root locus. Okay? And so we can design the R closed loop transfer function based on the what? The k value. Okay? And so we can set the different k values in here, and so we can determine the how our system react or the response to the what? To the RS value on this closed loop function. This is why we need to learn about the root locus, because if we can use the root locus and then we can set the proper values of the k in terms of the what? The settling time, overshoot, or the what? The peak time. Okay? So this is the basic representation of the root locus. And so in the section 2 we need to talk about the properties of root locus. Okay? Firstly, just remember that for a given closed loop system like TS, k times gs divided by 1 plus k gs hs. Okay? And so what's the characteristic equation of this transfer function? The characteristic equation is given by k times gs and hs. Okay? Our dynamic response is based on this equation because we have the denominator in here just like this one, and so if we want to change the R response, dynamic response, time response of the R system, we need to change the pole location in the what? In the S domain. Okay? Because in the S plane we have the real and the imaginary parts of this system, and so this characteristic equation creates the what? The poles. Okay? And so this poles creates the dynamic response of the R terms. Okay? So if this is the case, and then we can write that this equation can be generated. K gs times hs is equals to the 0, because if we want to create the poles, we need to equalize the R equation into the what? Into the equals to the 0, and then this creates the poles, right? Okay, and so we can deduce that these terms into the what? The k gs times hs must be equals to the what? Minus 1. Our second deduction coming from the what? These terms. Okay? So this transfer function, for example, s squared plus k s plus k plus 10, for example, can be generated in here. This must be equals to what? The minus 1 in here, because this is the general solution for a given what? The k, in order to what? In order to draw the root locus. Okay, and so if the gs and hs can be given in here, and then we can just what? Change the k value with what? With one condition. It always must be into the what? The minus 1 in here. Okay, so our third deduction is that the k times gs and hs must be equals to the minus 1, or if we have this nomination 1 times in the polar coordinates, we have the 2k plus 1 times 118 degrees value in here, in order to what? 1, 2, 3 and blah blah blah. Okay, and so we have the magnitude values in here just like this one. Just remember that in the vector notation we have the magnitude and the theta value, and so if we change the k value with the based on the what? The equals to the minus 1, and so we can select the proper values of the k, but this is the magnitude. Okay, and so the other terms is coming from the what? The degree values in here, just like this one. Okay, and so in degree values we can generate the what? The minus 1 with based on these equations. Okay, and so in the closed loop form, in absolute notation, we have the k times gs times hs is equals to the 1, and the angle of these terms k times gs times hs must be equals to the what? The q 2 times k plus 1 and 180 degrees in here. Okay, and so this yields us to what? This general solution, 1 divided by gs and hs. Okay, this is the absolute values of the what? The generation of the k. And so the other terms in here, just like this one. Just remember that if we want to design the stable system, we need to use these two properties. One of them, this one, the other term is this one, in the root locus techniques. Okay, because if we select these terms, and so for example k can be chosen as the 50, but these 50 values as the k may be stable or not, but these two condition is satisfied, the stability is guaranteeing in root locus techniques. Okay, please guys read the Nice book 8227 section. Okay, if you want to understand more detailed information about the root locus. Okay, and so what's the meaning of this angle and the magnitude values in here? First thing, we can graphically analyze these concepts. Like, for example, if we have the system just like this one, k times gs times hs can be equal to the what? The k, s plus 3, s plus 4, and s plus 1, and s plus 2. Okay, we have two poles and two zeros in here, and so we can write that ts, or the closed loop transfer function, can be obtained with what? The k, s plus 3, s plus 4, and 1 plus k times s square plus 3 plus 7k times s and 2 plus 12k's. 12k, okay? So, this is the R closed loop transfer function. This is the open loop. Just remember that, open loop, and this is the closed loop, okay? And so, how can we draw the root locus? Firstly, we can draw the S-plane in here, sigma and JW. This is the S-plane, guys, okay? So, what is the poles of this system? Firstly, we have the S plus 1, S plus 2. Okay, we have two poles, minus 1 and minus 2, right? And also, we have the two zeros, 3 and 4, right? Minus 3 and minus 4, right? Okay. So, this is our the open loop pole location in the what? In our algorithms. Okay. So, just remember that if we want to assign the any closed-loop transfer function, this is the characteristic equation, right? And so, for example, if we design the any system as the roots of the what? The minus 2 plus j3. For example, this represents to the what? The zeta, omega n, and VD value is given in here. And so, just remember that this can be equalized with what? The TS 1.1, or overshoot values is maybe equals to what? The 20 for this root. And so, if we set our closed loop transfer function possessing these roots, and then we may have the what? The transient response in accordance with the what? With these two parameters. Okay, and so if we want to design a controller in here, and then we must what? We must locate these poles on this S-plane, because our closed loop function, closed loop transfer function, must have these roots in order to what? Behave in terms of the what? The TS is 1.1 overshoot 30%. Okay, 3%, 20%. So, if we have this notation, and then we can write these values in here just like this one, but I'm sorry, it's not true. And so we create the J3 and the what? The 2. Okay, we need to assign or locate this pole at this nomination, but we have the open loop poles and zeros in here. So, how can we use the polar coordinates in here? It's simple. We can just draw what? The lines in here, just like this one. Okay, we have the lines in here. Okay, so each line possesses the what? The theta 4 and theta 3 and theta 2 and theta 1 in polar coordinates, right? Okay, and also we have the what? The length of these terms, L1, L2, L3 and L4, right? And so this L's is the M, is theta, is a theta in the polar coordinates. Just remember from the previous what? Previous slides. This is the polar coordinates. Okay, and so how can we calculate the values of the theta and L1 values in here? Firstly, the K can easily be found with what? The K is equals to 1 divided by M, or in another terms, hold the multiplications of the what? The pole length, and the whole the multiplication of the zeros. length. In another terms, the k can be calculated with what? The pole lengths in here, -2, -1, L3, L4, and L1 and L2. We have the zeros length. This is just geometry. The k can be calculated by using these terms. In order to what? In order to set this pole into the what? -2 plus J3. Okay? If you are using the poles of this equation, and then you can find out what is the best values for the what? For the k. If you choose the k in accordance with this one, and so we can provide the system this transient response. Okay? Or, for example, if we want to calculate the whole the terms in here, for example, square root 2 times 2, 1, 2, 2, and 2 times 1, 2, and 1, 22, which is equals to what? The 0, 3, 3. Okay? Maybe if we are using, or if we are selecting the 0.32, 33 in here, and then the R closed loop transfer function behave like in this domain in here. Okay? And so, how can we calculate the theta values? In the root locus, if we have the zeros, just remember this term, we have the positive value. Poles has add the negative values. For example, we have the 1 zeros in here, theta 1 plus theta 2, but theta 3 is a pole. We need to subtract this theta 3, and this is the theta 4. Okay? And so this must be equals to the what? 118 times 2k plus 1. Okay? These are the second conditions in here. This is the first condition. Is coming from the what? In these terms. The absolute values of these terms represents to the what? The polar coordinate amplitude. K, GS, HS angles can be created from the what? The zeros and the poles. Okay? Just see that. But in every case, we cannot set this characteristic equation. If you are choosing the k is into the what? The 0.33, and then the pole of this system is equals to the what? The S minus 2 plus J square root 2 divided by 2. Because the R system either not satisfy this condition or this condition. If we want to have a stable system, we must provide this one and this one in geometrical notation in the root locus techniques. Okay? So, any question about these terms? This could be complex for you guys, but it's simple. We want to what? Draw a signal, or we want to place the sum root at this root locus techniques. In order to what? In order to set the closed loop transfer function denominator, or the characteristic equation. And then we can set the parameters of the TS overshoot values and create the what? The pole, or desired pole. And then if we have the open loop zeros and the poles, and then we can create the what? Draw the polar coordinates in here. L1, L2, L3, and F4. And so this creates the what? The angles. Just like this one. And then we want to calculate the what? The proper K values in here. Just like this one. And so we also calculate the what? These degree values, which equals to what? 180. Right? Because these two conditions are satisfied, and then the R system is stable, and our system is located at what? The desired poles in here, just like this one. But we cannot easily set this K value because this geometry maybe does not permit to the what to locate this pulse. From the what? From the system properties. Okay? And so, if we want to design our system, and then we need to use the proportional control based on the what? The root locus techniques. Okay? So, any question? Did you understand what I'm saying? Everything? For example, the bilge? Just answer me, please. Okay. Okay, and so we need a break right now, and at the 1 p.m. we will start the example of this root locus. Okay?